Welcome to Stat 400, Week 2 at the University of Bridgeport. This week, we're going to continue with descriptive statistics, take a look at distributions, and some tips on our code. So, think of the notion in aviation terms of IFR and VFR, instrument flying rules and visual flight rules. This meaning we will be relying on statistical metrics relating it to instrument flight rules, and visualization, the visual flight rules, to tell us what's going on with our data. So descriptive statistics continued. We will learn this week standard deviation, variance, skewness, and kurtosis. Standard deviation, denoted by the letter sigma, measures the amount of variation or dispersion from the mean. We see the formula there on our right-hand side, where we see that the standard deviation is the difference between x minus x bar, x being each observation, x bar being the mean. We square those differences, sum them all up, and divide it by the number of observations, n, minus 1. We take the result of that, take the square root, and we have the standard deviation. So for now, it would seem a little bit, complicated. It's new. But just think about this is that we're looking at differences of each observation from the mean. And we're doing some form of an average of those differences. So let's think about an example of grades. If we took the standard deviation of grades of a class, meaning how different is each grade from the average grade? A low standard deviation would indicate that most grades are similar. Conversely, a high standard deviation would indicate that grades are very different from each other. Variance. Variance, very similar to the standard deviation. We look at the formula to your right. It is the same formula, just without the square root. What this means is that it can never be negative. It is a non-negative number. And again, it's talking about dispersion from the mean. How dispersed are each observation from the mean? Skewness. Skewness, again, maybe a metric that is new to many people. However, you've heard the word skewness before. And skewness means the lopsidedness of a distribution of the data. A negative skewness means that, again, skewness is a metric where we see, again, if it's 0, we don't have a skew, meaning that tails on the right and on the left are very similar to each other. A negative skew, which is your bottom right graph, would indicate that the tail is on your left. A positive skew, your graph that is top right, means that the tail is on the right. Now, interesting is that the mean and the median will behave always the same way when you have a positive skew, and it will behave the same way when you have a negative skew, meaning that when you have a positive skew, the mean will always be greater than the median. If you have a negative skew, the median will always be greater than the mean. Moving on, kurtosis. Kurtosis is talking about how peaked or how flat your distribution is. So kurtosis equal to 0, you have a distribution that is nor peaked nor flat. It would be called more normal, and it would be a normal distribution if we had also skewness equal to 0 and other metrics that would make it a normal distribution. So if we have a kurtosis greater than 0, means that a lot of values are very similar to each other. If we have kurtosis less than 0, meaning that it's more flat, it would indicate that we have very similar number of observations for each bucket of different values. Continuing with that example of the grades, if we had all the grades being A's, we would have a very, very high kurtosis, greater than 0. Conversely, if we have grades of A, B, C, D, and F, and we have equal quantity of students obtaining each one of those grades, we would have a very negative kurtosis. Let's take another example. Let's look at the income in the US. This is a distribution that the skewness is what? Positive or negative? If we go back to our slide on skewness, we see that it looks like this one, a positive skew, where again, the mean should be greater than the median. Let's go back and take a look. So here we see the income of the US. It has a positive skew, and the kurtosis, if I had to guess, it probably would be greater than 0, and it's centered around these values over here. This is where you would have your peak in some way. This note is not a peak. It's saying the graph says that these two groups include households reporting income greater than 200,000, approximately 4% of the household. The reason why they lumped them all together here is that if they would have had the same size buckets going on and on, we wouldn't have, the slide would be very, very, very big. So again, we have a median household income of 51,000. Why would they report the median and not the mean? Because we know that the mean is greater than the median when we have a positive skew. I don't know the answer. However, one likely reason could be that when you report the median, you're saying that half the people make less than 51,000, half the population, households, make above 51,000. So it's a nice metric to look at. The mean is going to be a lot higher, and it is skewed because of the very high income people. Very high income meaning above 200,000, and I'm sure there's a few people there with making millions and millions of dollars, which is a rare event. Moving on. So now we have the tools to describe distributions, but distributions have names and they have purposes. So these are statistical distributions that we're talking about. And in this class, we're going to review and understand a few of them. So distributions that we're going to be looking at in this class is the normal distribution. It is meant for continuous variables. We have the chi-square distribution, which is meant for categorical variables. We have the Poisson distribution, count variables, meaning discrete occurrences, such as births per year. You would say, oh, but wait a second. Isn't counts also a continuous variable? It is. However, they're integers because you're counting things, and you're counting things that cannot be fractions. And again, you can't have half a birth. Either there is a birth or there's not a birth. And last but not least, very important, the binomial distribution. It is referring to dichotomous outcomes such as buy, didn't buy, live, die, etc. So as the course progresses, we will go deeper into each one of these distributions as the topic arises. For now, try to classify variables into the distribution that they would likely fall into. Moving on, let's have some tips in R. So last week, we looked at how we can do a summary of all the variables within a data frame. But what happens when we want to do the summary of just one variable within the data frame? Then we would do this piece that you see right here. Summary, data frame name, $, variable name. In other words, before we would just write the word summary, an example, the data frame census, close parenthesis. That would give us the summary statistics for all the variables within the data frame census. But if we just wanted to see the summary statistics of age, we would write the data frame name, $, which is a separator, but not only is it a separator, it's also indicating that what's coming next is the variable name, which is, in our example, age. Another piece of a tip here is how do I create a duplicate of my data frame? This so I don't mess up the original one. And why would you mess up the original one is that as the course progresses, you're going to be doing calculations and modifications to variables, but you want to keep a copy of your original data intact. So the easiest thing to do is to create a duplicate of that original data frame and work on it, that copy. To do that, you just write your new name for a data frame, less sign, minus sign, which is kind of like an arrow pointing that you're going to dump something into new name. New name is going to be in R, it's called an object, new name. And you're going to put into that object called new name, you pick your name, original data, whatever your original data is. And that would be your 2 tips for the week. So now it's time to do this in R.